Hey, what's up everyone? Jason Turley here, and recently I've been going through pwn.college, which is just a great online free resource that has a bunch of different lecture videos about computer security and computer science. It's hosted by a couple of professors at Arizona State University, and the great thing about it is they have all these different lecture videos and PowerPoint presentations and a bunch of additional resources, and then different challenges like capture the flag-esque challenges that you can solve. And you do rank up and you get points, and it's called pwn.college, but it's more of like a dojo learning environment, and you see that you can get different colored belts as you advance and you progress through the course. It's really, really great material, and like I said, it's 100% completely free. So if you are interested in anything like computer science or computer security and exploitation and reverse engineering, it's not a bad resource to check out. So I've been going through the shellcode injection section of this course, of this resource, and I have some notes here on the right hand side, so forgive me if I peek and look at them throughout the video. But today we're just going to be writing a very basic shellcode in x64 assembly, and there's no real practical purpose to do this. If you do want actual shellcode to run on a system, it might make more sense to just use something like MSF Venom or go to like a shellstorm.com. I think that's what it's called. So if you do want actual shellcode for different architectures, those might be better options than just writing your own from scratch. And we see Shellstorm here has a bunch of different architectures and whatnot, and we can just grab shellcode from here if we really needed to, like if we found a bug or an exploit, or if we found a bug or vulnerability. So to get started, instead of actually writing the x64 or the x86 assembly, I think it might make more sense as an introduction to write the shellcode in a higher level language like C or C++, and then compiling it and assembling it and seeing what the compiler gives us versus what we might write ourselves. I think that'd be a nice little exercise. So let's open up Vim. I'm gonna make a simple file and just call this shell.c. Make our main function. Every C program needs a main function, some type of entry point, so the computer knows where to begin the execution from. And we're going to have one line, execve, and we need to pass this a few arguments. So let's look at the man page for execve, and we can do that in Vim just by doing colon to bring up the Vim menu, I guess. And then exclamation point to say we want to run some type of system command. So exclamation point man exec ve. So here we go, exec ve, execute the program. We see that it's a standard C library function, which you can get from libc or library C. The synopsis simply states that if you want to use this program, you should import this library, uni.std.h. You should import that header file. We'll come back to this synopsis in a second, but let's scroll down just a little bit and make sure everyone can see that. And let's look at the first paragraph of the description. So execve executes the program referred to by path name. This causes the program that is currently being run by the calling process to be replaced with a new program. It gets a newly initialized stack, heap, and initialized and uninitialized data segment. So all this is saying is it takes your current program, whatever you're running, and it replaces the address space with a brand new program. So there's a concept of like fork exec wait. So if you have your main program and you want to go off and do something else, you might use fork to spawn a child, or like basically a clone process or a different process entirely to do something else. That's something you might see typically done with like malware. It might fork off and spawn a different process, and then the parent, the one who created the fork, would wait until the child completes the task. But maybe that's a video for a different time. This is all about shellcode. So we have execve. This is very similar to system, the system library call, the libc system call, where you can just execute some other program. This is another way to do it. So execve is going to take exactly 3 arguments. Path name, so what program do you want to execute? You would put that here. And then what environment, what what arguments you want to pass to the program. So the argument vector and then any environment variables. So the arguments and then environment variables. So that might seem a little complex, a little complicated, but I promise you it's not. So for our first argument, we want the path name. We're going to be executing bin sh, very simple. And for the other two, we want null. We're not going to include any arguments. We're not going to include anything from the current environment. And we're going to leave it like that. Let's :wq to save and quit. And let's try to compile this with GCC tech s to specify I want to output assembly and not like an actual elf header or an elf file to be executed. So the name of our program and then the name of the output file. We hit enter and we do get a warning, implicit declaration of function execve. We did not include that uni.std.h header file that we saw earlier. So it is giving us a warning. It's like, hey, I'm not entirely sure where you got this function from. Perhaps you want to include the header file, but it's just a warning. So we're going to ignore it. So here we see an error, null. Null is not defined. So null is actually just a macro. It's basically a placeholder or like a variable. So if I did something like pound define null 0, and now I try to compile this, that works just fine. We still get that error from before, but we do have our shell. Actually, I'm going to rename this from shell to shell.s, give it a little extension. Now if I run file star on everything we have here, we have our C source code, and now we have our assembler source. Alternatively, if I open up my Vim session again, instead of defining null to be 0, I can just go in here and change these to 0 because they are the same thing, at least in C. I'm not sure if they're the same in something like C++, but here null and 0 mean the same thing. It means an empty value or essentially like no value. Let's recompile this. We don't really mind that warning too much. And the only reason we're not including the uni.std is because it's like the C preprocessor. So let's copy shell.c to shell2.c, open up shell2. Now let's actually include it just to see what happens. uni.std.h. Save and exit. Now let's compile this. So we no longer get that error, but if we do ls.l anything.s, we see the file size is a tiny bit different. If I look at the C preprocessor of shell2.c, we see that it prints out all this stuff. So if you're curious what this is uni.std. It's that header file that we imported. But if I do the same thing on the first one, we see we really don't get that much, right? So the C preprocessor, what does that do? It's going to expand any macros you have. So we had define null 0. It's going to expand any macros. It is going to expand any header files that you include. And that's what's going on here. So it is making the binary a little bit larger and more complicated than it needs to be. So we're just going to work with shell.s. We don't really care about shell2 in this instance. So let's cat out that assembly code. So it's not too many lines of text. We see here the file name. Let me make sure everyone can read this. Zoom in. So we see the file name shell.c. That's the C source code. We see a section being defined for RO data or read-only data. We see a label being defined, label C0 with our string, bin sh. That's the thing that we want to actually execute. That's the binary, that's the program on the system that we want to execute. We see something here, global main, because right in C, you need some type of main entry points. You need the same thing in assembly. You can name this something else. It's really just symbolic, but here we're naming it main. Main is a function. So we scroll down here and what's being executed underneath the main label. So we see some garbage, start process. Ooh, this syntax, this is AT&T syntax, right? The order of the registers are how they are, and we see these percent signs. I personally think it's a little bit hard to read. I think it's a little bit ugly. So I'm actually going to recompile this code, shell.s, and this time I'm gonna add the flag tac masm equals intel. We still get that warning, don't really mind. So now when we cat it out, we get the intel syntax, which I think is just a little bit cleaner. It's a little bit easier to read and it makes more sense in my head. So here we get this label. We see the epilogue. It's just setting up the stack. It's pushing the base pointer onto the stack, and then it's setting the base pointer equal to the stack pointer. And then we see these arguments being created, right? So these registers are basically just variables. That's all they are. They're just variables that live within the CPU, the central processing unit. We see EDX and ESI are being stored 0. And the reason for that is, let's cat out shell.c. Those are the two arguments, the argument argv in the env p, the environment pointer, and the argument vector pointer. So those are being set to 0. And here in RAX, we see the instruction LEA, load effective address. So whatever in this label, LC0, grab that and store it in RAX. So if we scroll up a tiny bit, we see in LC0, the string -h is being passed. So all this is doing is setting up all the arguments for the execve function call, right? It's not a system call. I almost said it's a system call. Since this is a C, so this is a little bit confusing, right? So we have man execve. This is a standard C library function, but it's also the name of a system call. So C, they like, or Linux, I guess, they like to have the function, the libc function calls being the same name as the system calls, right? So it can get a little bit confusing if you think about it like that. So it's loading the arguments, -h with the 2 null values. We see that here. And then it's going to call execve as it finds it in the procedural linkage table, right? So it's calling execve just like we did here. And then it's deallocating, it's doing the epilogue, right? So we set up the stack here with a push, and now we're cleaning it up with a pop, and then we return. And there's some other like directives and whatnot that aren't too important necessarily to understand how this program is running. But essentially that's it. So this still isn't, let me remove all these shell 2s because we don't need it. I can't execute this because this is still assembly code. Even if I try to make it executable and run it that way, you know, it's not going to work because that's assembly. Change mod -x shell.s. If we want to actually run this, the quicker way is actually just really compiling it and then take out the tac-s flag, shell.c output shell. Now if I do file star, we see now we have an elf executable, ls, and we can just execute it. So there, now we have our shell. So that's cool. We learned how to do that in C, but now let's actually try to do that in assembly. So I'm gonna make a new file, just called the shellcode.s. And now we're gonna be doing actual x64 assembly. If we really wanted, we could peek at the shell.s file that we have here, and we could glean some information from this file. We see here, since I compiled it with the tac masm equals intel, it now added this little label here, intel syntax, no prefix. So I'm going to use that as well. Oops, that grabbed a lot. Because I like using intel syntax. We also need a global, I'm going to call it underscore start. Here they call it main, but we're just going to call it underscore start for our label. And now we can actually get into the interesting part of the x86 shellcode that we're going to make. So we want to do execve, not the library call, but this time we want to do the actual system call. And in order to do that, we're going to use this resource called syscall.sh, which, as it says right here, it's a resource to navigate the Linux system call table. So they have different APIs here. They have ARM 64, x64, which is what we're using, and then x86. So if you're curious about what the differences are, it's just 32-bit and 64-bit. So if I click on x86, these are all 32-bit registers. And they start with E, so EAX, EBX. If I go over to x64, very similar, but now they just have R in the beginning. So RAX, RBX, RDI, whatnot. So here we see the first row of the table denotes what is in the columns. So for example, for the system call read is indexed in the table as system call 0. So system call 0 is read, system call 1 is write, and so on and so forth. We want the one for execve. And then here, the arguments in order are RDI, RSI, and RDX. So all these are just different variables, right? And if you've done C or Python before, or JavaScript or any programming language, you're familiar with what a variable is. In this case, these variables are just registers, which are just actual pieces of memory in your CPU, in your central processing unit. And they can store different values. So all registers are variables, right? They're not that sophisticated. And then in x86, they just want to pass the variables in these registers in a very specific order with RDI, RSI, and then RDX. So let's do a control F and let's search for execve. And we see here that it's syscall number 59, or in hex, syscall number 38, or 3B rather. Hopefully everyone can see this. So we're looking at this right here, execve. We know this will be RAX. This will be RDI, which is the first argument, the constant character file name, or the path name, what program you want to execute. This one is RSI. I might have to scroll to the top just to confirm. Yeah, RSI and then RDX. So go back there. So RAX, RDI, RSI. So pretty simple. So let's actually make this into our shellcode. So we want to set the, and before we actually code, maybe it's more helpful to like add some type of comments of what we want to do. So execve -h 00 is the actual program we want to execute. So let's set RAX equal to the system call number, which is 59. Syscall num. It's always good to add comments in your code in general, and this is especially true for assembly. So now we need to start setting up our programs. You need to start setting up the execve system call, and we do that by setting the registers. You can do it in any order, but we're just going to do it in the order we saw in that table. So now we need to actually store bin-sh inside the RDI register. And there's a few ways you can do this, but I'm just going to create a label called the bin-sh and then use .string to tell the assembler that we are going to be passing it a string function. And this automatically adds the null terminator bit. Oh my goodness. It adds the null terminator bit that C strings need, just so they know when to stop reading. So load effective address of RDI. And this syntax will look a little funky, but we're going to do the opening and closing square brackets. And now I'm going to do RIP, which is the instruction pointer. So if we're executing code on an assembly line, wherever it's currently being executed at, do that, and then add the offset bin-sh. And that's just going to help ensure that it can always find this bin-sh string when it's being run and assembled. So we'll just say first argument is bin-sh. So lastly, we need to set the next two registers to 0. And there's many ways you can do this. First, you could simply just do move RSI 0, or if you want to be fancy, you can do XOR RDX with RDX, and that will also set the registers to 0. So far, so good. We have all of the arguments set up. Now we just have to do syscall. So if we look at this code, we have 59 being set to RAX, which is telling the assembler, I guess, telling the CPU to get ready for a system call to execve function. We're setting RDI to binsh, so we want to execute binsh. And then we're setting the next two values to 0. You can do that by just literally moving the value 0 into the register, or you can just do an XOR, right? So if you're familiar with bitwise operations and or not XOR, if you XOR a number with itself, it'll always return 0. Let's save and quit. This looks good to me so far. And let's assemble it with GCC. We can do no standard library because we're not using any standard library calls. This really doesn't matter here, but I'm going to add tac static because I don't want this to be a dynamically created binary or anything like that. We're going to feed it shellcode.s, and then the output, let's just name this shellcode.elf, and we'll see why in a second. Let's hit enter, cross our fingers, and it compiled successfully. If I just do ls-tech-l on the shellcode, okay, we see that. We see it's colored this way because it's executable. So why is this executable and when we compile it like this? So if I do file shellcode star, we see that shellcode.elf is actually an elf executable, right? Before, when we compiled our C program with GCC tac s and then shell.c output shell.s, that gave us an assembly file, right? That gave us assembly. But this time we assembled it and we got an elf header. We got an elf executable. If we were to look at the header file of it, or the top like magic bits, shellcode.elf, type that in the head, we do see that is a .elf file. It's statically linked, x64. It's not stripped of any debugging information. If we wanted to, we could strip it with like the strip command, but we're not really going to do that. So if I execute shellcode.elf, it works very similarly. I do get a shell, right? ls, we see everything here. You know, I could cat etsy password or etsy shadow, anything like that. So if we exit out of it, so that's cool. So that's how we go from our assembly to our elf file, but this still isn't shellcode. It's not something that you would pass to an exploit payload that you have necessarily. It's an elf file. So if you want that raw output, you need to extract the text section. So let's do object dump tech D to dump it, and tech M to specify the Intel syntax of shellcode.s. Object dump is crying. Why is it crying? Do I want the C file? Oh, shellcode.elf. There we go. So we see, let's scroll up so we can see everything. Here, let me pipe this into less so it's easier to read. So we have our shellcode.elf file. We have a section called note GNU build ID. And here we have the text section, right? So this is actually the hard, you know, the meat and potatoes. This is the shellcode that we wrote, right? So we see the OX33B, which just means decimal 59 that we saw over here, 3B. So we see the system call number being loaded into RAX. We see our binsh being loaded into RDI, and we see RSI and RDX are being set to 0 with two different techniques. And the reason you might not want to do move RSI 0, the reason you might not want to hard code 0 and moving that into RSI is this right here, right? So if this was like shellcode that we were passing to an exploit that we wrote perhaps in Python, and then we're using this to exploit some type of remote server. So let's say there's a remote server or a binary that had a buffer overflow vulnerability, right? It had a stir copy where it read an unlimited number of bytes, or like get string where it reads an unlimited number of bytes into a fixed size buffer. If we have our shellcode and our shellcode has zeros in it, what happens when a C library function encounters a 0 byte or a null byte? It stops reading it. So for example, if we were to pass this shellcode into an exploit payload, right? We're taking advantage of the vulnerable get string vulnerability, for example, or the vulnerable stir copy function, for example. It would read all these bytes until it hits these zeros, and then it would stop, and it would not read the rest of our shellcode, and we would not get actual remote code execution. So that's why doing something like XOR to get the value of 0 is preferred, because those null bytes, those 0 bytes, aren't being generated. So both values are being set to 0, and then we call system call, right? Before, if we looked at the other assembly instructions, if I cat shell.s, we see call, where's it at? We see call is being executed. That's because this is a libc function, but over here we see system call is being instructed because this is actually a true system call. It's not using the standard C library in any way, shape, or form. If the C library is up here, our assembly is down here. It's underneath it. It doesn't have access to those library functions. And those library functions, they're really just wrappers for system calls usually. I found this nice write-up on like man system calls. So if you just do man to system calls and whatnot, you can see here, where is it at? Often, but not always, the name of the wrapper function is the same as the name of the system call that it invokes. So system calls are generally not invoked directly, but rather via wrapper functions in glibc, which is the standard C library, or some other library. And then it tells you for details of direct invocation of system call, you can see this page here. So system calls and library functions are very interesting. It does get a little bit confusing because they are named the same. execve and execve can be a system call, or it could be a standard library function. So we see here binsh is being created. And these are just the actual like ASCII representations of the string. So if I go somewhere like cyberchef, While that's loading, it wouldn't be a bad time to go out and buy some sweet merchandise so you can look good and feel comfortable while you're hacking. So I type binsh here, binsh, and then I add the recipe to hex. We can see that hex is being generated here, right? Hopefully that's big enough for everyone to see. There we go. So we see /binsh. If I highlight just this one character, we see slash is represented as 2f, b is 6.2, and so on and so forth. So this is the actual hex that's being passed to the computer. And we see that here, 2f, 6.2, so slash, and then b. And, it's telling us, hey, these might be bad characters. It might be something you want to look out for, or maybe the terminal just can't interpret the character. I'm not really sure. But that's what our assembly looks like. That's what our elf file looks like. And if I do that again, so the reason this isn't shellcode is because it has all this junk here, this GNU build ID, that section. The section we really care about is just the text section, right? The starting points, and then binsh, that label we created. So all we want is this. We want this right here. It's going to be a lot smaller payload, which might be interesting to us. And this is all we truly need. So if we want to extract that, we can with something called object copy. We're going to do tac dump section. And I need to refer to my notes because I forget how the rest of the command goes. There we go. So we want object copy dump section, just the text file, right? The text section that we saw here. We want just the text. And we're going to call that shellcode.raw. So let's grab this and just paste it in. Why not? Now if I do an ls-l on shellcode, we see a raw file was created. If I run the file command against that, zlib compressed data. That's interesting. So it's raw data. I cat it out. Looks a little weird. So if I actually try to run this, it's not going to work, right? If I make it executable, not GCC, change mod plus x shellcode.raw, and I try to execute shellcode.raw. It's not going to work, right? Because this is a binary file. We want that elf file that we saw earlier. So change mod minus x shellcode.raw. But if we were making an actual exploit, this is what we'd actually want to pass to the payload. Until shellcode.raw. Oh, it's not an elf file, so it's not going to recognize it. So that's basically it. I just wanted to showcase and highlight some of these resources. I think syscall.sh is great. I think pwn.college is a great resource for learning these things. Again, it's free to sign up. I did want to highlight something called godbolt.io real quick. So godbolt, which is a compiler explorer. So you can do this. So what we did is we just created a C file, right? We created our own C file, and then we assembled it with GCC, and we played around and we looked at the assembly. But that's not very fast, especially if you want to just test something quickly. So you can come to Godbolt and just do it here. Let's make it large enough for you guys to see. And we see I've set this up here, right? I included uni.std header file, and then we have the main function, and we have execve, everything that we saw in our own source code that we created. And over here on the right hand side, you can choose what architecture, what language you want this to be compiled in. We're just going to do the latest version of x64 compiled with GCC. And it's going to create something very similar to what we saw over here. I'm not sure what GCC version I have. I have 13.2. So if I swap this to 13.2, perhaps it'll be identical. But yeah, so you see very similar, right? They have a string -h being defined as label LC0. We're setting up the stack with pushes and moves. We're creating our arguments to be passed with 2 null values of 0, and then we're setting EDI to be our -h, and then we're calling execve. So that's dang near identical to what we saw over here, cat shell.s. Very similar. Very, very cool. So that's really it. I hope you guys thought this was kind of neat. I've been playing around with pwn.college, and it's a great resource to learn like shell coding. For practical applications, you don't really need to write shell code by hand like this, but perhaps you work in the gaming industry, or you want to work in the gaming industry, or you want to work in exploit development. Every now and then, maybe you need to write your own bits of assembly. So doing this exercise is a great way to kind of know how assembly works. Knowing about the system call table, that's something new that I learned from doing this exercise, right? I didn't know the system call was a table that could be indexed with different values. So I just think that stuff is kind of neat. Hopefully you guys found this useful. For a very short exercise, a very short program, it was kind of a long video. But hopefully you guys gleaned some information and, can walk away better hackers, better programmers. And if you want to program and be comfortable, you can always check the link in the description to get some merchandise and be comfortable while you code and whatnot. So let me know in the comments below what you guys thought, any improvements or suggestions, whatnot. As always, take it easy and see you guys in the next video.